Modern agricultural planning requires evaluating thousands of contiguous acres, calculating yield potentials, and mapping environmental risks down to the square meter. To build a complete picture of a single field, agronomists have to pull soil metrics from the USDA, cross-reference water quality parameters from the EPA, and overlay satellite vegetation imagery from NASA. Because these agencies do not share a unified format, combining their data requires analysts to spend weeks wrestling with disjointed APIs and writing custom Python scripts just to force the coordinates to align. The recent repository approval of the LeafEngines Agricultural Intelligence Plugin, version 1.0.2, bypasses that entire manual process. Instead of exporting to web dashboards, spatial intelligence generates directly on the QGIS canvas. An empty topographic grid receives stacked layers, soil composition, water density, and vegetation, locking into place. Natively querying agencies avoids API bottlenecks, immediately outputting a fully styled, topologically accurate vector layer. Securing the official Plugin ID 4987 designation from the QGIS repository indicates that the underlying code has passed compatibility, security, and basic functionality reviews by the platform's maintainers. This places the tool directly inside the native plugin manager, making it instantly discoverable and installable with one click for tens of thousands of global users. Embedding advanced AI capabilities into the primary software environment used by environmental scientists and government agencies drastically reduces the time between raw data collection and physical field deployment. To see how this accelerates a GIS workflow, we look at the initiation sequence from the analyst's terminal. The analyst can trigger a macro-level data pull across massive regional datasets by simply inputting a standard county FIPS code. Alternatively, they can launch a highly localized microquery by clicking directly on a specific field boundary polygon within their map. This flowchart maps the background process triggered by that single map click. The initial input signal instantly splits into 3 parallel data fetching pathways, targeting the USDA, the EPA, and NASA. The USDA pathway extracts localized soil composition data, isolating critical metrics like pH levels and texture classifications for that specific coordinate range. Simultaneously, the EPA pathway retrieves regional water quality indicators, mapping both current contamination levels and historical trends. The NASA and NOAA pathway pulls real-time satellite telemetry, generating vegetation indices like NDVI alongside current water stress overlays. LeafEngines functions as a central translation layer, mathematically resolving the conflicting projections, resolutions, and formats of these 3 separate data streams. Automating this spatial join eliminates the need for manual reprojection, historically the most error-prone step in multi-source geographic analysis. Unifying these isolated agency databases into a single, topologically exact workspace provides the necessary statistical foundation for running accurate predictive AI models. Standard large language models struggle with geographic tasks because they process text semantically, lacking any inherent awareness of rigid spatial boundaries or coordinate systems. LeafEngines bridges this gap by utilizing the Model Context Protocol, or MCP. This animation demonstrates the MCP architecture in action. A standard natural language text query is broken down and actively translated into a set of strict coordinate-bound polygons and executable database parameters. Operating directly inside QGIS, LeafEngines acts as an open-source MCP server, exposing the underlying GIS functions to an external intelligence model. This creates a hybrid workflow. QGIS enforces the strict mathematical reality of the map, while an AI like Claude executes complex conversational logic over the data. An analyst can ask the model to identify fields exhibiting severe water stress, and then cross-reference those specific polygons against current carbon credit feasibility metrics. As the analysis concludes, the plugin automatically generates and populates a complete GIS attribute table attached to the new vector layer. The AI processes the combined soil, water, and climate data to populate this table with localized crop suitability rankings for every individual parcel. It calculates precise nitrogen, phosphorus, and potassium fertilizer recommendations, constrained to the exact acreage of the user's selected polygon. Delivering these insights as mathematically sound, queryable GIS layers rather than loose text summaries forces the AI output to adhere to the strict requirements of professional agronomy. The theoretical capability of an AI model only matters if it can function where precision agriculture actually occurs. The industry calls it the deep canopy problem. In remote environments, far from cellular towers or server infrastructure, cloud-dependent AI tools simply fail to connect. For an intelligence layer to be viable in the field, it must be built on an offline-first architecture. The LeafEngines plugin achieves this through a proprietary algorithmic optimization called TurboQuant. This comparative bar chart maps the physical hardware requirements. The TurboQuant optimization delivers a 6 times reduction in memory consumption compared to standard unoptimized processing models. This massive reduction in resource weight directly enables an 8 times increase in localized inference speed. By shrinking the memory footprint, complex spatial inferences that previously required heavy cloud servers can now execute entirely on local, ruggedized field laptops. In GPS-denied environments, teams maintain their analytical capacity through aggressive offline caching, downloading targeted satellite layers before leaving connectivity zones. The system supports heavy batch processing, allowing field workers to run massive analytical loads entirely offline, syncing their results back to the master database only when network access returns. Cutting the mandatory tether to cloud servers ensures that high-level predictive modeling can be deployed to the actual locations driving global food security. Integrating an MCP server into QGIS creates immediate secondary effects across the open-source mapping community. The plugin is mapped to a specific set of metadata tags: soil, environmental, satellite, agriculture, NDVI, and carbon credits, indexing it instantly for institutional researchers searching the repository. The official repository approval signals to universities and conservation NGOs that the core architecture has been vetted by third parties and is safe for institutional deployment. The platform utilizes a freemium model. The free tier gives local extension services immediate, zero-cost access to basic satellite imagery and initial AI query capabilities. Large-scale operations requiring premium environmental data layers, continuous API access, and advanced carbon credit modeling drive the commercial conversion pathway. This enterprise usage feeds directly into the paid subscription tier of the broader SoilSidekick Pro ecosystem. By positioning itself inside QGIS, LeafEngines integrates seamlessly into the exact software that government agricultural agencies already mandate, bypassing the friction of introducing a completely new platform. The experimental label on version 1.0.2 explicitly leaves room for rapid iteration and community feedback. It acts as an open invitation for developers to build their own custom node integrations, such as automated pipelines for ingesting high-resolution drone imagery or IoT sensor data. By embedding complex semantic logic natively into the world's most ubiquitous mapping platform, the industry moves past the slow phase of manual data collection and into the deployment of automated, edge-computed spatial intelligence.